Hey everybody, I want to talk to you about exponential functions really quick. Well, hopefully really quick. Also, I'm trying out the new Zoom text function, although not on the first couple pages. You'll see what I mean when we get to the end. So exponential distributions are another kind of continuous distribution. They model a few things. That's not why we're interested in them. I want to talk to you about exponential distributions for a couple of reasons. One of them is that there is no CDF in your calculator for exponential distributions. I don't know why. They could easily have one and it'd be useful. They've got Poisson, which is related to exponential. But it's so that you can get some practice just using the calculator as just a calculator and not putting in functions into the calculator yourself rather than using the predetermined ones, which is a useful skill in and of itself. And then the other reason is the connection with Poisson, which I'll talk about at the end. It's an interesting connection. So yeah, let me first describe what they are. So an exponential distribution is something of this form where f of x, so the probability function, or excuse me, the function that defines the probability for any value of x, is me to the minus mx, where m is 1 over the mean. So this is the population mean of this distribution, and a connection between those two. If a is 1 over b, then b is 1 over a. One way to think of this is that if a is the reciprocal of b, then b is the reciprocal of a, right? If a and b are fractions, this is pretty easy to see, right? 2/3 is the reciprocal of 3/2, and 3/2 is the reciprocal of 2/3. It's a little less obvious with integers, but still true, right? 0.25 is 1 over 4, so a is 0.25 and b is 4. But it's also true that 4 is 1 over 0.25, right? So 1/4 is 1/4, so 4 is 1 over 1/4 is what that says. I find that my students often don't realize this connection, but that is true. And the reason this is relevant is that sometimes you will be given one and have to find the other, or vice versa, right? You might be given m and have to find mu, or might be given mu and have to find m. In both cases, all you do is find the reciprocal of m to get mu, or the reciprocal of mu to get m. Okay, so here is the area function for an exponential function, or for an exponential distribution. So if I have some number k, and I want to emphasize that k is not the mean. I know I've drawn it in the middle, but it's just so I have lots of area to shade on both sides. If k is just any number that's bigger than 0, because exponential distributions only go greater than 0, then the area to the left of k is 1 minus e to the minus mk, and the area to the right of k is e to the minus mk. And if you are interested in finding out where these formulas come from, I can show you, but it requires calculus. So if you're interested, let me know and I'll be happy to show you. If you want to do it on your own and you know calculus, this is actually, you just integrate this function. That's all it is. And if you don't know what I'm talking about, then when you learn to integrate, that's what you'll end up doing. Yeah, but so these are the functions that we're going to plug into our calculator. And again, I don't know why there isn't a CDF for this. It's not like it'd be hard to add into the TI software, but there isn't. Sheets and Excel will do these just fine. They have exponential.dist, I think, in Excel, or exp.dist, and then Sheets is expon.dist, so expon.dist. I don't know. That seems like a weird place to cut off that word, but anyway. Yeah, so that's how we're going to find areas, and of course that's how we're going to find probabilities. And let's do it. So here's where I'm trying out the text function. Looks okay here, not so great on the next page. So Juan buys a new computer, and Juan is interested in computers, and so he knows that the hard drive in his computer lasts an average of 5 years, or the brand of hard drive in his computer lasts an average of 5 years, and that its lifetime is exponentially distributed, which is a thing that is true about hard drives in general. X is going to be the length of time that Juan's new hard drive will last, right? So it could be anywhere. It could fall apart tomorrow, or it could last 20 years. We don't know. And we want to find the probability that it lasts at least 4 years, lasts less than 7 years, or that it lasts between 2 and 6 years. So I'm going to do what I always do, and I'm going to draw my function. Right? So draw my distribution. So I've got my distribution here. I know that mu equals 5. Mu equals 5. So that means that m is 1/5, which is 0.2 in a calculator, if you want to put that in. And so I want to find the probability that x lasts more than 4 years. So let's do that. So here's 4. And I'm looking for this area here. I don't want to shade too much because I'm going to have to erase that. So what I'm going to do is I'm going to go to my calculator. And I'm going to put in the function with k equals 4. So the function I'm going to use to find that area is this one, e to the minus mk. Right, so m is 0.2 for us, and k is, for the first question, 4. Right, I'm looking for the area to the right, so I'm going to choose k equals 4. So let's go to calculator. There we go. Whoops, I need to clear all this stuff off. Okay, so I want to put in e to the minus mk. So second function, e to the x. So this is where second function is, or this is where e to the x is. E to the power of negative m, which was 0.2, times, or k, which was 4. There we go. That's the probability, 45%, that it lasts more than 4 years. That's it. That's all there is to it. Let's go write that down. So this is, I've been using pink for my answers. So this is about equal to 0.4449. Forgot what it was. Where's my calculator? Oh no. Oh no, I've lost everything. There it is. Yeah, 4493. Okay. 4493. There we go. Okay. Probability that x is less than 7. Well, I'm going to do the same exact thing, but shade the other side, right? So where's my eraser? That guy. Let's see if I can avoid erasing everything. Success. All right, so I'm looking to shade to the left of 7. So 7's over here somewhere, I guess. 7, and so we're going to be going this way. This should be a pretty big number we're looking for. So let's go jam that in the calculator. Calculator. It's 1 minus. Calculator. Hello. It's not letting me use my number pad. This is weird. Okay, that was really strange. What the heck? E to the minus, oh, now it works. 0.2 times k is 7 this time. 75.34%. Go write that down. About equal to, oh no, it's not pink. That's no good. .7534. All right, so 75.34%. And now for this one, we don't have a formula for this, but what I'm going to do is the following. I'm going to sort of combine the formulas that we have. If I want between 2 and 6, so here's 2. That's still a race. Oh my goodness. You'd think I'd never used Zoom before. I swear I use this all the time. 2 to 6. Okay, so what we're going to do is we're going to go either both left or both right, and I'll show you what I mean by that. So here I'm going to go both right because the formula is slightly simpler. So what I'm going to do is shade in everything to the right of 2. Right, so that's the area to the right of 2. And then I'm going to subtract off the area to the right of 6. Right, we're going to chop this out here. I should have done it this way. Right? And by doing that, we'll be left with just the area between 2 and 6. And of course, you could do this to the left as well. We could do everything to the left of 6 and chop out to the stuff to the left of 2 to be left with the things between 2 and 6. But I'm gonna go right because the formula is slightly simpler, right? That's the one with no 1 minus in it, so that's the one I'm going to use. Yeah, so this is going to be the area that we're left with there is going to be e to the minus mk. So in this case, case 2, right? So we're going to go minus 0.2 times 2. And then we're going to minus the blue area there, which is e to the minus 0.2 times 6. And so that's what we're going to do. I'm going to just go type that into the calculator and see what we get. So calculator. So we're going to have e to the minus 0.2 times 2 minus e to the power of negative 0.2 times 6. And of course, you could write this as minus 0.4 minus e to the minus 1.2, right? That's totally fine. I'm just putting it all out there so you can see the formula. And also, you're welcome to just type it in like this. So we got about 37%, which seems plausible given our other answers. So 36.91%. So it's about equal to 0.3691. There you go. That is how you find areas in an exponential distribution, right? you're gonna want to remember / write down these formulas, and how to use them. You'll get a little practice on the homework. Yeah, that's really what I want to say about finding areas with exponential distributions. Oh, I guess I do want to show you how to do that in Sheets and Excel. I'm just going to show you in Sheets because it works the same in Excel. So I think the command might be different in Excel. I don't remember what it is, but for Sheets, it is expon, E-X-P-O-N .dist, exponential distribution function. And it works the same as the other ones, right? So lambda here is the thing that we called m, not mu. This is m. Your book calls it m. Sheets calls it lambda. I don't remember what Excel calls it. But it works the same as the other distribution functions in Sheets, where it will either tell you the y value if you turn cumulative to false, or if you turn cumulative to false, or it will tell you the area, which is the thing we want, up to that point if you have cumulative on true. So for us, let's see what the probability that it was. What we say, less than 7 for part B. So we have x is 7. That's our k. Lambda was 0.2, and cumulative we want true. And 75.7534, exactly like we said. Right, so it does take you have to do a little bit more, I think, in the in Sheets and Excel. It's not too bad, right? It just, now keep in mind it only goes left. So if I wanted to find greater than 4, which was part A, right, I'd want to do equals 1 minus exponent.dist with x of 4, lambda of 0.2, and cumulative true, and 0.4493, just like we found when we used the calculator. So there you go. That's how you do it. You do it the same way in Excel. I don't remember what I think it's exponential.dist in Excel, but you can look it up. Sorry, it's been a little while since I did it in Excel. All right, so the connection between Poisson and exponential is pretty interesting. And please bear with me on this next page. It's a little ugly. I'm trying out the new text function, and it doesn't like Greek letters. Sorry, it's so sloppy here. I put lambdas in it. So the way I did this was I typed it in Microsoft Word and then put it in, copy and pasted it in here. And lambdas turned into black squares or black circles, and mu's turned into open circles, white circles with a shadow. I don't know why, but that's what it looks like, and I couldn't make a change back. So here you go. So here's the connection between exponential and Poisson distributions. If you have a Poisson event that with an average frequency per unit time of lambda, then the wait time between those events is exponentially distributed, and it has a mean of 1 over lambda. So mu equals 1 over lambda. And of course, m would be 1 over mu, which is just lambda. So for example, harkening back to the homework, if you have worldwide shark attacks that are Poisson distributed with a lambda of about 1.58 attacks per week, which is about what you should get on the homework, by the way, then the time between the attacks is exponentially distributed with mu is 1 over 1.58, or about 0.63 weeks. So in other words, you should have a wait time between attacks of about 0.63 weeks, which you might say to yourself, well, that's actually seems pretty obvious, right? Like if you have 82 attacks per year, for instance, then the average time between attacks is 1 over 82 years. And it's true, like that is in fact pretty clear if you think about it for a second. The interesting thing here is that if the events themselves are distributed in a Poisson fashion, then the wait time between those events is distributed in an exponential fashion, which is interesting information. So that's the connection Poisson has with exponential. And it felt a little weird to talk about Poisson distributions without talking about exponential distributions. So we're doing both, and exponential distributions also give you some practice with the calculator and sheets and whatnot. Yeah, and I think that's all I really want to say about exponential distributions. They're not super complicated. They're, they look like this. Calculating the area, you do really have to do some thinking some of the time. And I really, really recommend drawing your exponential distributions. It's really helpful, especially since when you have to do something like this stuff right here. It really helps to have a visual aid to help you along. Yeah, like I actually find it kind of hard to visualize without doing the visual aid, right? Because you have to figure out which direction you want to shade and which one you want to subtract from which, right? Which one's bigger, and then you have to remember the formulas, and like that's a lot to put in your brain all at once. So it really helps to get some of it down on paper so that you don't have to do everything in your mind. You can do it. You can use a visual aid to help you. So yeah, I strongly recommend that. You should definitely do that. And other than that, I don't think there's anything I want to say about exponential distributions. So I'm going to go ahead and stop there, and I'll see you guys in the next video.